Okay, so the next talk will be given by Sirui, and it's on symbolic compilation with a new cool library.
Yeah.
Please go ahead.
Can you hear me? Okay, I think so. So hello everyone, and thank you for the introduction. Today I'm going to present our work, Grisette, which is a symbolic compilation library for building program reasoning tools. So this is a work with my advisor, Bodík from Google Brain. So let's start with some background. So the symbolic compilation is a useful technique for building program reasoning tools, such as verification and synthesis. So it is a process that transforms a given program into its logical encoding and delegates the reasoning to the off-the-shelf SNT solvers. In this task, we have the corresponding assertions for the programs, and the solver searches for the desired programs or inputs. So in many of these tools, unlike test generation, the desired path can be very sparse. So this requires us to reason about most or all the paths to solve the problem, and requires careful tuning of the symbolic compilers to efficiently compile all program paths at the same time. So there are different ways to compile multiple paths into constraints, and two of the extremes are symbolic execution and bounded model checking. So symbolic execution is a technique to enumerate the program paths and compile each path to constraints. So for the program on the left, we execute the program by representing the input as symbolic values. And here are alpha and beta. And when the program executes an if statement, it explores both paths and maintains the path conditions. And each path will be compiled to the conjunction of the path condition with a negated assertion. And here, this formula is unsatisfiable, meaning that the assertion cannot be violated for this path. And after exploring this path, the system will explore all the paths and will find one buggy path. So this exploration of the execution tree is exponential, causes the path exploring problem, and does not scale when we need to explore all paths. So bounded model checking tools also compile the program symbolically. But instead of enumerating all the paths and executing them separately, it merges the program states when the paths merge. So here we can merge the values for y with the if then else operator, and we can do the same thing for x. Then the program is compiled to this formula, which is equivalent to the disjunction of all the formulas for the path. So it is satisfiable, meaning that there exists at least one path that fails this program. So with path merging, we can avoid the path exploring problem, but the resulting formula can be harder to solve. So there have been ideas to merge less to make the formulas easier to solve. So these systems usually try to preserve constants and simplify the formulas. So we present more ideas on how these paths should be merged and propose a new representation for symbolic values. It generates smaller formulas and runs faster than the state-of-the-art algorithm in both the compilation and solving time. We implemented the algorithm in a reusable symbolic compiler as a purely functional typed library called Grisette in Haskell. So we know that it's important to be efficient, but why being a library is also important when no previous tool for all path scenarios does this. So let's talk about the previous systems. So with the development of the solvers, so the symbolic DSL have been more and more widely used for program reasoning. So such symbolic DSLs are essentially domain-specific languages extended with symbolic constructs. So these symbolic DSLs are usually easier to reason about while still being very expressive. And in program synthesis, a DSL with symbolic constructs like program hosts has already become a standard technique. So Rosette is one of these systems to simplify the development of such symbolic DSLs. By providing a lifted core of Racket, Rosette allows the reuse of this efficient symbolic compiler with a simple and intuitive interface. So a tool designer can get high-performance program reasoning tools by just implementing an interpreter for the DSL with Rosette. So there have been many tools developed with Rosette with this workflow. So they are solving a wide range of different problems like database or file systems. So these have shown that Rosette has made program reasoning more accessible to wider communities and not just for PL peoples. But however, we still find something that we can improve in the system. So the first is that Rosette does not have a clear boundary between the lifted and unlifted parts. So this may cause confusion and make debugging harder. So the typed Rosette approach tried to resolve this by adding types to Rosette. But their approach is still a partial solution. It is still restricted by the dynamic nature of a racket, and is imprecise due to the implicit lifting in Rosette. A natural idea to improve this is to directly build a similar tool with a strongly and statically typed language. But however, it is unclear how to just port these tools into other languages, as Rosette, along with other tools, usually has design decisions specific to the host language, with a heavy use of the meta-programming facilities. So the third is that, like many other symbolic compilation tools, Rosette is an impure language, and the assertions are compiled using global states. So ideally, we want a small core that is very generic and composed well with common functional programming techniques. So we need to mention that there are existing purely functional formulations for symbolic compilation, but none of them is designed for the all-pass scenario. So instead of partly lifting the host language, our system, Grisette, is simply a library on top of the language. So being purely functional is usually a good idea for portability and safety. But however, being pure means that we cannot maintain the assertions or other program states globally, and we have to maintain them with the symbolic values flowing through the programs. So this would make the symbolic values more complex and stresses more on the symbolic representation and the merging algorithms. And it turns out that the previous representations may have performance degradation when merging complex data structures. And we have implemented the Rosette's merging algorithm in Haskell and run several benchmarks on them. And for the slowest one, we observed a 14 times slowdown, even if Haskell is usually a faster language. And this convinced us that we need to design a new representation to accommodate to the functional programming scenario. So these are our design goals. We want a system that is efficient, effective, and usable. It should be fast both in compilation and solving, and should provide a friendly programming interface. And this is the outline. We will first introduce our new representation, and we will then introduce our empirical results. And then we will show our programming interface by building a simple program synthesizer in Grisette. So let's first look at a simple example. So this is a pseudo Haskell code extended with symbolic values. In this code, there are complex data types, like lists and operations on them. So to generate better formulas and support advanced features easier, we want a representation that allows us to call the head function as a symbolic compilation time, rather than delegating it to the solver. So this is one of the most important design goals in some previous systems, like Rosette and multi-SE. They get to a similar solution, and we call it mutually exclusive guards, or MAG representation. So in the MAG representation, the lists with the same length are merged, and the lists with the different sizes will be kept separated and will be associated with their path condition. So we can then apply the head function to the concrete list, and this eliminates the list values and avoids delegating them to the solver. So the downside of this encoding is that the path conditions need to be mutually exclusive, and we need to construct many new nodes to keep them disjoint, especially when there are many branches. So in this example, even if we can share the same subnodes, there will be 7 extra nodes to construct. To reduce this redundancy, we choose to use an alternative representation, and we call it ordered guards representation. So instead of keeping the conditions disjoint by using more complex path conditions, with org representation, we use this if, else if, otherwise encoding, and the guards are mutually exclusive by nature and are simpler. And here we can see that there will be only 2 new nodes constructed and has much lower overhead than MAG. However, we know that most of the previous systems allowing evaluating the head function as a symbolic compilation time are using mag. So why does this happen when org seems to be simple enough and works well? So let's compare where these two representations duplicate subnodes. So we have already shown that the disjointness introduces larger formula in mag representation. The org representation, however, does not work well if we need to reorder the values. And this will bring the disambiguation conditions or the disjoint conditions back. So we want to know whether mag or org has more overhead. And the research question here is whether disjointness or reordering creates more duplication. To answer this, let's think about the merging of two org containers. For this simple program, we assume that A and B are represented by the following two org containers. So how to merge them? It turns out that in the result, there could be only one order of the values, and we need to reorder the values in at least one org container to align the values. And here we reorder the values in B, and we get the result. The real problem is that with the org, when done naively, need to reorder the value on each merge. So this could make org perform much worse than mag. So for this problem, we have a simple insight that we can keep org containers always sorted and reduce the need for reordering. So by keeping this sortedness as a representation invariant, we will only need to reorder when an org container is constructed, and the further merging will not need to reorder. And this reduces the overhead significantly. And when it comes to complex types like tuples, which is everywhere in purely functional programming, we can also generalize this sorted org representation to sort by the concrete fields, align them, and merge the values with the same concrete fields. So the problem with this is that the merging algorithm needs to inspect all the values one by one, and may need to augment all the past conditions in the result. As the complex types are usually harder to merge, and it can make the size of the org containers grow bigger, the overhead of the merging algorithm in both constraint size and running time can grow a lot. So our solution to this problem is to introduce a hierarchical encoding and organize values in subcontainers. And for example, here we can organize all the values with the first field 1 in the subcontainer T1, and also the same for T2. And during the merging, sometimes we can simply treat the whole subcontainer atomically and not inspect the value or augment the past conditions in it. So this is still a linear time algorithm, but it can run faster and generate smaller formulas when merging complex types. So we have shown the intuition of our algorithm, but the actual performance has to be evaluated with an empirical study. So we aim to answer these questions. So is Grisette more efficient in both evaluation and solving? And why Grisette's constraints solves faster? So we perform our evaluation on 4 symbolic compilation systems. So we compared Grisette with Rosette before and after POPL'22, as they have very different handling of assertions. And to avoid the impact of both language performance and to evaluate mag in purely functional scenario, we also compared it with a variant of Grisette that is implemented with mag. We ported 5 tools for diverse program reasoning problems previously implemented in Rosette to Grisette. And this could also show that Grisette is reusable. So these 2 figures show that Grisette is more efficient than SOTA. The left figure is for compilation time, and Grisette is always the best. And the right figure shows the solving time, and Grisette is the best for the most time. So we have already discussed that the good compilation performance comes from the faster algorithm that accommodates the purely functional scenario. But we still need to understand why Grisette is faster in solving. To answer this question, we plot the term size versus the solving time for all the tool combinations. And we can see that in general, the smaller the term are, the faster the solving is. And if you look deeper into these figures and compare the points for specific benchmarks, we can see that Grisette pushes the points to the left lower corner and solves faster with smaller terms. So we show that our algorithm is efficient, but it cannot benefit people from the wider community if we are going to let the people write their own symbolic compiler with our algorithms from scratch. So we will show that Grisette is easy to use by constructing a minimal synthesizer without the need to care much about the details of symbolic compilation. So we will try to synthesize a single input function x to x plus c. And here we are just synthesizing the value of c. And we will use IO pairs as specifications, and we expect that the result to be x plus 3. And to build the synthesizer, we first define the DSL and the program space representation. So this definition looks like an expression type, but there are some key differences. So for the sint value, instead of using the concrete integer type, we choose to use the symbolic integer type to let the solver fill it in. And for the sadd and small, the sub-expressions are defined using this unim generic container. And this unim is just our org container, and it represents multiple expressions together, thus representing a space of expressions compactly. Then we can define the interpreter for the DSL. So it also looks like regular interpreters. Well, here you can use this ununi combinator to lift the interpreter to work with unim values to interpret the whole program space all at once. Then we can define the program space and do synthesis. The definition of the program space is also like the definition for a regular program. And know that unim is a monad, and we can use a return operator to wrap a single value in it. And we can then make this program executable by composing it with the interpreter. And we then run the program space on our input and construct the constraint that the result is 5. The solver will give us a model as it can find a solution to the constraint. And we can then print the synthesized program or get an executable version. So the evaluate sim function here evaluates the program space with a model. And the evaluate sim to conv function further converts this evaluate symbolic value to concrete integers. So Grisette provides many such facilities for tool building, and it's better included and is ready for building real-world tools. A careful listener may notice that Grisette doesn't implement symbolic compilation for common imperative constructs such as mutable arrays. And this seems like a huge limitation. But however, our approach is in line with the purely functional programming approaches and works with something like state monads. And here, unim is a monad. And its operations are all generalized via type classes. And these generalized operators will also perform efficient merging. And we've got a few instances already, and they have benefits. For the state transformers, it takes about 30 lines to support it. And you can just write the interpreter for an imperative DSL with a state transformer. And we also provided support for free monads and combinators, functors for trampolines, and also all the MTL transformers. And if you want to reason about the coroutines, you can use trampolines or delimited continuations. And this is usually not available in previous systems. And there are also some additional benefits that I do not have time to elaborate on, like using static types for performance tuning, and we get 8.7 times speed up on codec, or using memoization to further accelerate the execution of 4 benchmarks. So please see the paper for more detail. And Grisette is open sourced with BSD3 license, available through GitHub and Hackage. And we will continue to maintain and improve it and welcome you to try it for your own project. And we welcome any kind of help to build the tool better. And thank you.
Yeah, thank you for the talk. Are there questions? Except thumbs up. No questions? Okay, I have a question. Okay. First of all, you mentioned the solve construct that you had in one of your examples for the synthesizer. Called solve
This-
there. Yes.
Yes.
Which kind of solvers do you use on
SMT solvers. So this there is a solver config. So I hided it. So here you can configure it to use Z3 or bool actors or CVC4 or all kinds of this. So currently we are using the Haskell SBV library as a backend, and we can use any solver supported by that.
Okay, awesome. Perhaps any further questions in the audience? Okay, I have perhaps one more question. When you said when you use the org representation, you don't have to reorder all the time.
Yes.
But does that mean that the initial ordering becomes somewhat important, or did you see this in your benchmarks, for example?
Well, yeah. So here we make the initial ordering always a sorted one. So we don't have to reorder it in the future.
Okay.
Yeah.
Good.
So, but if you do not use a canonical order like this sorted, it will be ordered in an arbitrary way, and when they are merged, you have to reorder them.
Last chance. Any? Yes, there's a question. Please wait for the microphone.
Hey, thanks. Symbolic compilation looks cool. So these examples were for synthesizing integers. Can you synthesize larger terms with this framework, like whole functions or function bodies?
For the function bodies, usually we synthesize them as a DSL using a DSL encoded in Grisette. So it's like we are usually using the deep encoding so that you can print that functions. And if you just use those shadow embedding, it is not possible to print that in Haskell, and that's usually not the way we do that. And by the way, Grisette also supports the uninterpreted functions. And if you want to synthesize those functions like from integers to integers, you can just use that.
All right. Any further questions? You also mentioned that you formalized parts of this in Coq.
Yes.
Does this include the runtime bounds, or did you formalize?
We formalize the complexity bounds. Yeah.
Okay.
So we prove that it's linear time.
All right. Cool. So unless there are any further questions, let's thank the speaker again.